So, so today I'm giving a guest lecture, filling in for Ryan. My name is Venkatesan Guruswami. So Ryan said he had one lecture on randomized computation, so I'm going to follow on with what he did, and I think the plan is that this will be the the second and last lecture on randomized complexity. Though you'll see some, I'm sure, some related things in the remainder of the course as well. Okay, so just recap, I think, of what you saw last time was these classes RP, randomized polynomial time, and co-RP, and you saw some examples of problems in either of these classes. For example, primes naturally fits in co-RP, and many other problems like that. So today we're going to make a definition which is slightly more general than each of these things. Would anyone like me to recap these notions? Okay, but I'll recap the notion of a probabilistic Turing machine. So you have this PTM, probabilistic Turing machine, and the idea was, basically there are two transition functions, delta naught and delta 1, two transition functions. And this was defined this way, though I'm going to give an alternate view of probabilistic Turing machine shortly, but this view is nice because it exactly mimics what you saw with non-deterministic Turing machines, where you had two transition functions, and at each step you picked one of them non-deterministically. So you somehow miraculously could search over all paths. So it's not a realistic model of computation. Whereas randomized thing, basically at each step, suppose you start, this is the start configuration, and there are two. So we just assume that at every step you use randomness, and of course if at some step you don't want to use randomness, you can just literally copy the configuration trees in both places. So you go to one of these two configurations. So you can really visualize this whole process as a tree. And then you finish the computation. At the bottom level there are various nodes which are accepting and rejecting, and these classes are defined based, these complexity classes are defined based on the accepting rejection behavior at the last layer. Okay, and the picture you should have is that you start the computation here and you're literally doing a random walk on the tree. At each step you go left or right with probability half each. Okay, so that's, and the transition, so and really the coin toss dictates which transition function you apply at each node. So that's really the model. So now we come to an important class called BPP, bounded probability of error probabilistic computation. So this is a new class. So it is basically all those things. So we'll say that the language L is in BPP. So again, it's going to be defined with respect to the same notion of a probabilistic Turing machine, but we are going to allow two-sided error. Okay, so let me just say this is two-sided error probabilistic polytime. Okay, so a language L is in BPP if the following happens: if there exists some probabilistic Turing machine M, we call it N actually, N, such that the following happens. One, if for strings in the language, so how did we define, for example, co-RP? We said that for strings in the language you always accept. So every one of the, if X is in the language and you do this computation, every one of these leaves will be accepting. So it doesn't matter, you don't need to be lucky with your coin tosses. On the other hand, if X is not in the language, half of these will reject. So if you just kind of walk randomly with probability half, you will get the correct answer. So now we are going to relax that by allowing error on both sides. So we'll say that if X is in, I think the probability over n's coin tosses, that n of X accepts is at least 2/3. Okay, so what would a natural definition be? We want strings in the language to be accepted more often than strings not in the language. Okay, and of course if you simply throw a coin without doing any computation, you can get half for both, because you could just flip a coin and say yes or no with equal probability. Okay, so really somehow the idea is that you want to separate these from half. So for strings in the language you need to be above half. For strings below not in the language, you want to be below half. Okay, and 2/3, 1/3 is just a convention, and as we'll see shortly, the choice doesn't really matter. For X not in the language, probability that n of X accepts is at most 1/3. Okay, and that's the definition. So it's a two-sided error computation if this property holds. Okay, any questions? So again, in that tree view, the way you should think about it is that if you do the computation for a string in the language, at least 2/3 of the leaves will be labeled accepting in the configuration tree. Whereas if a string is not in the language, at least 2/3 will be named rejecting. You could have more which accepts or rejects, but you at least have this guarantee. Okay. All right. So immediately you probably realize that this is a more permissive class because you also defined this class ZPP, which is defined as RP intersect co-RP. And I believe you'll do a homework problem saying that this is the same thing as having a machine which never errs. So it will always give an answer accept, reject, or I don't know, but it will not give a wrong answer. So if it says accepts or reject, you know that the answer is correct, but there's a small chance it will give up and say I don't know. Okay, which is also equivalent to saying it will always give the correct answer, but its running time may not be fixed. Its running time will be a random variable which is in expectation polynomial time. So perhaps you'll explore some of those equivalences in the homework problem, and all those are easy to prove. You're not just playing around with definitions. So now we have this hierarchy of classes, P which is in ZPP, which is equal to RP intersect co-RP. So of course it's in RP as well as co-RP. Okay, and this is of course contained in RP union co-RP. And the last thing which I want to add with this definition is that RP union co-RP is in BPP. It's a subset of BPP, because if a language is in either RP or co-RP, it's going to fit inside BPP. Okay. May not be, you might object. Someone say why it's not immediately true. So somehow these things say you have one-sided error. In BPP, I have two-sided error. But there's a little argument I need to make to say this. Okay, so I don't know how RP was defined, but presumably RP was defined like if it's not in the language, you accept with probability 0. So that's fine. That's less than 1/3. But if you're in the language, I think it probably said you're accepted with probability at least half. Right? Was that the way Ryan defined it, or? He also said 2/3. Well, he was prescient, so then it's immediate. And but even if you define it as half, as it's customarily done in some books, you'll see it doesn't matter because you can amplify these probabilities quite a bit. Yeah. Okay. So I'll just leave it at that. But one peculiar thing which I think probably you were told a couple of times is that in fact, while you have this hierarchy and probabilistic computation seems very powerful, a quite surprising thing is that all of these are believed to be equal. Though of course we can't show this. So we cannot show that any one of these is in fact an equality, but somehow we don't believe that, for example, even having two-sided error allows you to do more things than polynomial time. It might allow you to do things faster. You might save a factor of n in your runtime or n square or things like that, but it's believed that it's unlikely that you'll have a problem in BPP, which you don't know eventually how to solve in P. But of course, there are such examples. We definitely know problems which sit inside BPP, but which are not in P. But we think that we just haven't discovered the deterministic algorithms for those. Okay. All right. So one comment I'll make with the. So I'll make this comment about one-sided versus two-sided. So in some sense, we actually do not know really any natural problem where we benefit from allowing two-sided error. So somehow for all problems for which we know how to get a polynomial time algorithm, and there are a few prominent ones, primality used to be one of them till its deterministic algorithm was found. But in the search world, there are many problems which still we do not know how to do without randomness. By search, I mean it's not a yes/no answer, but you're trying to find something. So one prominent problem like that is that I can give you a polynomial and I can ask you to factor it. So integer factorization is hard, a lot of cryptography resides on this, but if I give you a polynomial and ask you to factorize it, so that can be done in probabilistic polynomial time, but we do not know how to give a deterministic algorithm. That doesn't quite fit in this language, in this framework, because it's not a yes/no problem. Okay, because it's you're trying to give an answer. Another very, very basic problem which we do not know how to solve deterministically, I can give you n, say 500, and ask you give me a 500-digit prime. So we do not know how to deterministically give a number which is a prime. And again, it doesn't fit this framework exactly because it's not a yes/no problem. It's a search problem. You're trying to output an answer. So that definitely in the search world, there are many questions which we would love to answer deterministically, which we don't. So it currently does add power. Okay, but in the framework we are sitting at, which is like yes/no problems, decision problems, really there is no natural problem which falls into BPP but doesn't also fall in either RP or co-RP. Usually just based on the problem, you automatically have one-sided error. Okay, but it's just a bit of a nuisance to say, oh, does your algorithm have false positive, false negative? I mean, I get, I find this terminology confusing. So we don't make a big deal out of it. I mean, if you get an algorithm with two-sided error, we say that's polynomial time. Though for most examples you will see, it will actually be in either RP or co-RP. Okay, so I'll just say that most language in BPP also in RP union co-RP. In fact, most I even say that almost all natural. Okay, but you can cook up some problems. So given that I can take a problem which is known to be in RP and I can cook up some versions which are in BPP but not RP, but they won't be natural. Okay, so again, that could be a nice trick homework problem. But you can cook up problems like this, but for most problems you care about, this doesn't happen. But again, we don't want to be nitpicky with which side you have the error and so on. So let's just somehow BPP is a more permissive class. It's nicer to work with. Okay, so one other thing I want to talk about is success probability amplification. So what do I mean by this? So right now you have a success probability of 2/3 for your, so you got to get the correct answer with probability 2/3. So you might want to get an answer which is even better than that, right? You might want to have higher confidence. So how are you going to do that? Any suggestions? Say I want to be correct with probability 99%. How will you boost your confidence in the answer? Yeah?
Run the algorithm multiple times.
Right, so run the algorithm multiple times, and what do you do with all its answers?
If the exception accepts, if it rejects, basically you're going to keep repeating the algorithm.
Right, so that would work for I believe RP or co-RP. I get confused. So it will work for one of those because the moment it gives an answer in one side, you're sure of the answer. But here it can err on both sides. Yeah? Yeah, so one natural thing is that it is correct more than half the time. So why don't you run it like 10 times and take the majority? Okay, so that's really the algorithm. So run n times. So n should be sufficiently large so that you get good confidence, and then take the majority. You can either take n odd, or if n is even, break ties arbitrarily. It doesn't really matter. Okay, that's going to be the algorithm, and it stands to reason that this should improve your confidence. And this is why whether you define that with like 3/4 or 2/3 or even half plus 1 over n, something teeny bit better than half, it doesn't matter. You can always amplify it to anything as close to 1. So I can really replace these with something 1 minus epsilon versus epsilon for definitely any constant epsilon. In fact, epsilon can even go down exponentially in n. Okay, so yeah, in fact, let me just actually write that. So you can replace these. So let me make some changes. So can replace, so let me just write it here, can replace 2/3 by 1 minus 2 to the minus 2x, something really, really close to 1, and 1/3. Okay, I mean, I'm just, that don't be too worried about the 2 and stuff. It's just something which is exponentially, if x has n bits, the failure probability is exponentially small in n. It's like 2 to the minus n, 2 to the minus 10n, something like that. And you can get that, and let me make this m because n might be confused with the input length. Okay. And this can be formally proved using, like, it can be proved using Chernoff bounds and so on, but in this case it is pretty special, so you can actually even just do a calculation. I don't want to belabor this point too much because we are not emphasizing probability per se in this class, but let me just, since the calculation is quick enough, I'll just do it. And but you can, if you don't fully get it, it's not a big deal. So what's the probability? But I just want to sort of impress upon you that you can get some pretty small probabilities like this. Okay, what's the probability that you're wrong inside? Suppose I give you some x. Suppose I give you some input x, you have to determine if it's an L or not. So you do this strategy, you run this algorithm, the BPP algorithm, which is correct 2/3 of the time, m times, and take the majority. Okay. What is the probability you're wrong? This algorithm, repeat plus majority is errors. So let's just give an upper bound on it. For you to be wrong, you need to be wrong at least half the time. Because if you're right half the time, you're going to be. So I can upper bound this probability by the probability that you're wrong k times, where k is at least m/2. Okay. So sum over k, at least m/2, probability that k trials are wrong. In fact, it's exactly equal to, this probability is probably equal to, but I don't want to worry about m/2 ties, so let me just say less or equal to. Okay. So clearly to be wrong, you must be wrong at least half the time. And if you remember, what is this probability? You're making m trials. Okay, each trial is wrong with probability a third. What's the chance that exactly k trials are wrong? So this is a binomially distributed quantity. Okay. So again, this probability is that basically you can choose the trials which you're going to make a mistake in m choose k ways. For each of those trials, you need to be wrong. So that's 1/3 to the k, and then remaining is 2/3 to the n minus k. Okay. You might object that the probability there, it could actually be even better than 1/3, the error probability, but that will only help you. So this is sort of your worst case. The worst case is when the algorithm is really wrong 1/3 of the time. If it's only wrong 1/4 of the time, you can even put 1/4 of the time. Okay. So this is exactly, this is at most this. And okay, now we need to bound this. It looks a bit scary, but if you don't care about really getting tight bounds, you can bound this very quickly. Okay, let me just do it in the following way. I'll just decouple this. If I take this part, sorry, this should be m. The summation of all binomial coefficients is at most 2 to the m. So certainly each of these guys is at most 2 to the m. So I can pull out a 2 to the m. And what about these guys? In these, I'm multiplying 1/3 at least as often as 2/3. So the largest this quantity can be is when k is exactly m/2. If k is bigger, that quantity only goes down, right? Because 1/3 is less than 2/3. So this whatever you're multiplying by is going to be at most this. Okay, everyone cool with that? And each binomial coefficient is at most 2 to the m, so you get this. And this, after you simplify, this can be written as 4 to the m/2, so you can just see that this is 8/9 to the m/2. And all these, the only thing you need to important in this is that 8/9 is a quantity which is less than 1, and you're raising it to a large power, so it's exponentially falling. So if you pick m to be large enough compared to your length of the input, so you can get this problem. Okay, as I said, I don't want to belabor this point too much, so if this was a little fast, don't worry about it too much, but this is just to say that the natural thing you think of does boost your success probability, and you can boost it very, very well. You can essentially make sure this is as good as correct answer with certainty, and which is also why randomized computation is considered almost, for practical purposes as good. So unless the application really demands complete certainty, these sorts of failure probabilities are just minuscule. All right? Any questions? Okay, so now I want to do a slightly, yeah, please ask me questions, yeah, if there's any. I'm also happy to go over this again, but it's not, don't get caught up if you didn't follow online every calculation, I think. But if you'd like me to, I can certainly expand on it. Right? All right, so now I want to, so we have this probabilistic Turing machine view of randomized computation, but I want to move to a different view, which is a little bit akin to the other view of NP as those things which have efficient verification. Okay, so you have this view of NP as having a certificate for membership which proves the membership of a string in a language. So I want to sort of move slightly towards that view. It's all pretty straightforward, the translation. So the alternate view would be that, so you have this view where you at each step you make a transition randomly, and this is the machine N. Okay, so the machine is going to walk down this tree randomly. I want to have another view where I have a deterministic machine M, Turing machine M, that takes randomness as auxiliary input. So what I mean by this is that this machine is given as input x, but we also pretend it is given all these random strings right at the beginning as input. And then such a machine can simulate this M basically by just referring to it. So you can just imagine a separate tape where this random string is written, and this machine can just walk on that tape, and each time it can run N by just using that random string as an input. Okay, so you should have this view that you are given this X, which is the input, and you also have this random tape R. This is the random. So given these two things, you can simulate N in a deterministic fashion. Namely, whenever N wants to toss a coin, you just grab the next bit from this random tape and go left or right. So now your computation is completely deterministic. Okay. Okay. So this M will take two inputs, M, X, and R. If you give it both X and R, it will give a deterministic answer. But of course, our input is only X. So the idea is that we will try to understand the behavior of M for a random R. So really, it's more or less the same thing, except that instead of doing these random things one at a time, you just assume that you toss, suppose you're going to need 100 random coins, you toss them all at once, keep them, and from that point on, you're a deterministic computation. Okay. Okay. So now let's write down the definition of BPP in this language. So L is in BPP if there exists a deterministic Turing machine M such that, which takes two things, such that for X is in L, that takes a two-part input. Let me just write it this way, X comma R, where that, of course, the R you don't want it to be too big, because you don't want to, these machines are supposed to be polynomial time, so they can't use more than polynomially many random bits. So you will just say that the length of R is at most a polynomial in the length of X. Okay. And the properties you want is that X is in L implies the probability over R in this whatever the polynomial may be. So you simply pretend that you feed M completely random string R, and then you ask what's the probability that M XR accepts. Is at least 2/3, or as I said, you can also replace this 2/3 by something extremely close to 1 by amplification if you want. And X is not in the language implies probability over R that M XR accepts is at most 1/3, and once again 1/3 can be replaced by something minuscule by amplification if you can. Okay. Does anyone, and this is exactly similar to the non-deterministic view for NP. So what did we say for NP? We said that there is a deterministic verifying Turing machine M, which takes two-part input. One is the string x, which you're trying to test for membership, and the y, which is the witness, or w, whatever you guys called it. And then given x and w, you can check if w proves that x is in L in polynomial time. And there the definition was that if x is in L, there will be some w which will make you accept. If x is not in L, no w will make you accept. And here we have just relaxed it in the sense that if x is in L, most of these r's will make you accept. If x is not in L, most of these r's will make you reject. So in some sense, this makes the search for that witness much easier, because you can just flip coins to find the witness. Whereas if I give you a 3-coloring problem and I ask you, is this graph 3-colorable? It's very hard to find that 3-color. Okay, so that's the alternate view, which I think is sort of a little bit nicer to think about, because we're going to quickly get, and again, the way the simulation works, the probability that n accepts a string over its coin tosses is exactly the probability that m accepts that same string over random r. Okay, we have just set it up like that. Okay, but somehow, this view is a little bit nicer to reason about, so you can work with. Suppose you have to prove some things about BPP, and we're going to prove a couple of simple things right now. You can use that view. Okay. Yes, question.
M needs to run in polynomial time?
Yes, M needs to run in polynomial time. Deterministic probable. Thank you. Poly time. Thanks.
Follow up to that. If it's polynomial in terms of x, you don't need the condition that r needs to be polynomial.
Yeah, that's right. Yeah, but I just wanted to emphasize that, so I wrote that. Yeah. Because that then will also get into some tricky thing, because we always measure polynomial time with respect to input. Then measuring it with respect to the first part is a bit of a change in convention. So might as well just say that second part is not too big. Exactly, again, this is exactly like in NP. You want the witness, the verifying Turing machine should be polynomial time. So of course it can't take a witness w which is longer than polynomial in x. Okay, so you're supposed to have a short witness which is efficiently verifiable. Okay, so that's your BPP. And of course for RP and stuff, with exact definition exactly the same thing. So for RP you will say the probability that MXR accepts is at least 2/3, but here you will say the probability it accepts is 0. So that's why RP sits inside NP, because it really respects the fact that if you're not in the language, in NP you should have no witness. Here you might have some small number of witnesses in the BPP case, but in RP you won't have that. Okay. And co-RP is the flip, and therefore it sits inside co-NP. Okay, so now let's see, so we know that BPP is bigger than RP and co-RP, so we can ask how big can BPP be? Can we place some upper bounds on BPP? Okay. And the point is, once you have this view, really the same, more or less the same upper bounds you can place on NP will also hold on BPP, because for the same arguments. Okay. So here is a little lemma, BPP. So if you have a language which has a randomized polynomial time algorithm, then it will also have a polynomial space algorithm. So BPP sits inside P space. Okay. And again, how are we supposed to prove this? We are given an inclusion, so we are supposed to take an arbitrary language in BPP and place it in P space. Okay, and the proof is really one line. So let's stare at this definition. You have a language in BPP. You have to prove, actually maybe I should just do, let's actually first do the weaker thing, which is x time. I mean, with this we can kill 2 birds in 1 stone, but let's do this. So let's say BPP is in x, for exponential time. So why is that? Why can you run a probabilistic time in polynomial time language? Why can you solve it in exponential time? There are 2 views. In the tree view, you can simply say, well, this tree is only polynomially deep. So you can literally explore the entire tree. Okay, but in this view also, it's kind of very obvious what you should do. The number of random coins you are going to toss is bounded by a polynomial. So you can try every possible random coin toss in exponential time by just literally brute force over this. Okay, so brute force over R. To find if x is in L or not. Again, the algorithm is simply try every possible R. That is going to take you exponential time, but that's not okay. That's okay because that's all I'm asking you to do. And you just estimate how many times you accept and how many times you reject. And you know that will be well separated based on the prompts. Okay, again the same thing for NP, right? NP was an exponential time because you could just search for the witness. And it's really here you can't just, the moment you find a witness there you're sure it's in the language. Here you have to kind of get some statistic. So you have to kind of do the whole thing. Okay, everyone good with this? And in fact, the same argument will also show that BPP is in P space, because looping over all possible R's does take you a lot of time, but it doesn't have to take you a lot of space because you can reuse space. So you literally just write down each possible R, and then after you try it, note that for a fixed x and R, it's a polynomial time computation. So it will definitely only take polynomial space as well. And then you try one particular R, and then you erase it or you increment it, and then go try the next R and so on, but you don't have to, you don't need too much space. You can reuse your space. Okay? So this is just reuse space for various R's. Right? So these are some easy consequences. So what else do we know about BPP? Okay, so at some point I'll draw a little diagram of all the different zoo of classes we have seen so far. Yeah?
So we want just P-space algorithms to decide L, right?
Yes.
And just because the randomized TM for BPP accepts doesn't mean that X is in L, right? Because there's a chance that it accepts even though X is not in L. So how do we account for that? When
you just keep a count. Sorry, maybe I should have been more clear. What you do is you loop over. So the algorithm would really be this: for R equals 1 to all the possible things, okay, run mx comma R, increment your counter if it accepts. Okay. And then you see if your counter is at least 2/3 the total number of R's or less than 1/3. Okay. You're given the guarantee it will be one or the other, and based on that you just give your answer. Right. So. And note that you can also be a little bit, I mean, if you want to, not that you are going to run this, but you can, the moment you accept more than 1/3, you're sure you're in L, and the moment you reject more than 1/3 of the time, you're not in L. So you can, probably terminate the loop a little early, but you're going to save factor 3 in your runtime at best. But really that's it. So you just run this, keep a count of how many times you accept, and see if the count is too high or too low, and that tells you if X is in L or not, and that's the correct answer. You're sure. Basically, this is just converting probability into counting. Right? After all, probability is just counting, in a normalized fashion, and that's what this is doing. All right. So one sort of a mystery in complexity. You have seen many classes. So now one thing you probably are wondering about is BPP versus NP. So what do you think about BPP versus NP? So there are two classes. It'll be nice if we know one sits inside the other. Yeah?
Well, if we believe BPP to equal P.
Yeah. Yeah, so I guess if we believe BPP to equal P, you don't expect NP to sit inside BPP. And because that will be great. All NP complete problems, you have a randomized algorithm with high guarantee. Who cares if you will fail to 3-color a graph with probability 1 in a billion, right? It's not, that will be great. So we don't expect NPs in BPP and so on. But then on the other hand, if you really think BPP is just the surrogate for efficient computation, we should be able to say BPP is in NP, perhaps, right? That won't, maybe shock anything. That won't lead to any thing. But that's not, sadly, that's not known. So it's not known. Neither is known. Or BPP. Or let me not confuse you. Let me just say you don't expect NP to be in BPP, right? So you don't expect that to be the case, but BPP is in NP, not known. So we cannot quite place BPP in NP. Okay, and the key problem is that, yeah, in the case when it's not in the, whereas RP, of course, we know to be in NP, right, but BPP we cannot place in. Okay, remember, I'm not saying this, this is not known, okay. In fact, much weaker things are not known. It's pretty shocking that we cannot, in fact, we cannot even, can't separate BPP from non-deterministic exponential time. So certainly if BPP sits inside NP, BPP will be smaller than non-deterministic exponential time, because I don't know if you probably at least were mentioned the hierarchy theorems, right? So if you have exponential time, you can do more than in polynomial time. But for all we know, BPP could be non-deterministic exponential time. So that is BPP equals not ruled out. So not only can't we limit the power of BPP, you know, by NP, but we can't even, if it was equal to a non-deterministic exponential time, I mean, that's like phenomenal. You can do everything you care about more or less in BPP, even that is not ruled out. So somehow it says that somehow our understanding of these random classes is not very refined. On the one hand, we believe it is equal to P, and I'll try to hint at why people say that in the, so maybe the last third of the class, just, you know, for culture and just information. But, you know, in terms of what we can actually prove, you know, there's a huge gap between what we believe and what we think the worldview should be and what we can actually prove. Okay, and this is probably one of the most alarming open questions in complexity, that we cannot separate BPP from NEXP. Right? It just sounds absolutely ridiculous, but that's the state. Let's see. But what we do know is that you might also, so now you might be a skeptic and you might look at these things and say, you know what, people's belief that all these things collapse to P, maybe that's not really the case. And you'll say, okay, maybe I'll separate BPP from P. So you can also, you know, you have to entertain that possibility, right? So, but what is known is that this is a theorem, so I won't prove this. No proof, without proof. It is known that if P equals NP, then P equals BPP as well. So it cannot be that non-determinism crashes to polynomial time, but somehow randomization really helps. Note that, okay, let me just write that down. P equals NP implies okay. And note that one way this would be true is that if you could just place BPP in NP, this will be trivially true, right? Because BPP will be a smaller class than NP. So if, then of course, you know, BPP will have to be sit between P and NP, and if they are equal, it has to be equal to P as well. But we don't know this, but we do know this fact. So in this sense, we kind of know that, you know, at least the direction is going the correct way. Non-determinism seems more powerful. So a contrapositive of this is that P not equals BPP. So if suppose you roll up your sleeves and say, you know what, I'm going to separate BPP from P, then you are solving the $1 million P versus NP question as well. Okay, so that's the contrapositive of this. So you can't separate BPP from P without separating NP from P. So in this sense, you know, really, you know, this is one little weakness we know, that BPP is perhaps an easier class, at least in terms of collapsing to P, though unconditionally we cannot quite say this. So unconditionally it is quite possible BPP is non-deterministic exponential time, and therefore not only contains NP, but it's you know, much bigger. Okay. Though I mean it's known to be very unlikely. Even NP in BPP is considered very unlikely. Any questions about all these little zoo of classes? Okay. So not that we believe P is different from BPP, but you know, if you're going to prove this, then that will imply P is different from NP. Okay, so now I wrote this linearly, so let's try to draw a little Venn diagram of these things which you probably have seen. We have quite a few characters in this zoo now. So we have at our beloved P here, right? So let's see. So I'm pretty bad at this. So you're going to have RP, and you have co-RP. clearly not drawn to scale. They should have the same size, I guess. And then BPP is here. And really, we believe all of these collapse to P. Okay? Now let's bring in NP. NP is, of course, contains RP. And we don't know quite its relation with BPP. So perhaps it contains BPP too, but we don't know that. So we're going to have to leave it like that. And then again, this co-NP has become a bit smaller on this side. Probably these things should be much bigger, right? Because we think NP is a much bigger class. And both of these sit inside P space, which is sit inside X, which sits inside NEXP. And the ridiculousness of what I said there is that we don't know if BPP equals all the way up there. We think it collapses to P. We can't prove it's smaller than the thing up there. And non-deterministic, I don't know if it was introduced, non-deterministic exponential time is exactly the analog of NP to P. So exponential time is those deterministic exponential time machines. Non-deterministic exponential time machines are basically non-deterministic Turing machines which can run exponential time. So it's a huge, huge class. Okay, that's the picture. And I guess you guys have done log space and other things also in the class, log space. So you also know things which go below this. You have NL and L inside this. Okay. So yeah, so if you want, you can draw those. So this is P, you have NL. Log space is those things which you can write with a constant number of pointers. Okay, pretty small class. And by the way, there are randomized analogs of log space. There's something called RL, BPL, and so on. I think we are not studying that in this class, but it's also quite fun and also a bit lot of work there. I mean, it definitely at the research frontier, and people thought at least maybe 5 years back that they were, while we didn't seem at all close to proving P equals BPP, even though we tend to believe it. People thought we were close to proving P equals L equals RL, but that doesn't quite pan out. Okay, but I mean, people still believe that's maybe in the horizon, maybe in the next decade. Though P versus BPP is not clear. Okay, so one other thing I want to say about BPP, and then I'll move into some information on why we think P equals BPP, or what kind of results can people prove in that regard, which makes them believe that. Okay, okay. Any questions? Let me pause for a second. So, in some sense, this is all the thing which we thought was central for you to know. So this is like required programming for this this lecture. But from the second half, or a little less than that, is perhaps some exploratory stuff. Okay. No questions? Everything is very clear? All right. So now let me do the following. So let me talk about circuits for a little bit. Another sense in which BPP is easy is that it has small circuits. Okay. So let me just say this theorem. So this, I'll state it in a way which is, maybe you may not so I'll prove some upper bound on BPP, namely it's easy in the sense of we don't know it's in P, but we know it's in P/poly. So this notation probably was not introduced. Okay, so this basically is the languages. So I'll just define it now. So it's a class of languages which has a circuit family of polynomial size deciding it. Namely, for each input length, there will be a circuit. So you all know circuits, obviously, just the usual circuits you know. But the key point here is that for each, the thing about circuits is that they have a fixed size, right? So they have a fixed input size. So when I have a circuit family, it's a family of circuits, one for each input length. But the point is these circuits could look very different for different lengths, and we don't care at all about how hard it is to come up with this circuit. We just care about this miraculous circuit exists. So P/Poly is all those languages which have a polynomial size circuits, and I believe you know that this can be a crazy big class because it even has like halting problem inside that, because you could just have a little circuit which tells you if the nth Turing machine halts or not as a it's a trivial circuit, it's either 0 or 1. We don't know how to construct it, but it does exist. Okay, so this is called non-uniform computation and stuff, which I believe we didn't touch in this class, but you don't have to get caught up in those technicalities. It's just class of circuits. Okay, so again, what we want to prove here is that if L is we can also, if this is confusing, let's just phrase it as if L is in BPP implies there exists a circuit of poly n size that decides. So for every n, there is a circuit of poly n size that decides L correctly on strings of length n. Okay, so for each n you have a different circuit. So at least in this sense, if you kind of think polynomial circuits are not so crazy, it at least has small circuit complexity. Okay. Whereas we don't think this is the case for example, NP. We don't think 3-SAT has this property that for every input length there is some small circuit. I mean, of course we can't prove it. We can't even prove it's not in P, but we somehow don't believe that it's going to have small circuits as well. It's like a genuinely hard problem. You can't even build a small circuit for it for large input lengths. Whereas any language in BPP is also easy in that sense. So it has a small circuit. Okay, and let's see if we can prove this. Again, I'll only sketch the proof. It's not so crucial, but okay. So one thing which I believe you know is that if you have a deterministic Turing machine which runs in some time t, you can form a circuit family which of size t square which decides the same thing. This is something you should have done in the Cook-Levin theorem proof and so on. So you can always compile Turing machines into circuits. Okay, there is a quadratic blow up which you can make t log t if you're more careful, but for polynomial, if you have a polynomial time Turing machine, you also have a polynomial sized circuit. So with that view, it seems we are almost in good shape because we do have a deterministic polynomial time Turing machine M, which, so let's draw a little, so let's try to do a proof sketch for what we just said there. Okay, the proof sketch is as follows. So you have some L in BPP, which means there exists this deterministic Turing machine, let me call it DTMM, with that property. So M XR accepts with probability. Okay, and now I'm going to use this part. Okay, so and let n be a, so minus 2 to the minus 2n if x is in L. Okay, and like fix an x whose length is, I mean, let x be an input of length n. So we know this is true, and then mxr accepts with probability at most 1 minus 2 to the minus 2n if x is not in. Okay, so this is something we know, and this is because courtesy the amplification. So we have a deterministic Turing machine which does very well when you randomize over the R. Now we have a deterministic Turing machine, we can compile it into a circuit. So we can have this circuit, let's call it C sub m, okay, and this is poly size. Because m ran in polynomial time, the circuit is going to run in polynomial, the circuit is going to be polynomial size as well. It is going to give you a yes no answer or accept reject answer. But it has two kinds of inputs. It has input x and it also has input r. Takes two inputs. We would like to build, this R is extraneous to, if you want to build a circuit for the language L, we shouldn't have this R. So the idea is we have to get rid of this R. Okay. If we get rid of this R, then we have a circuit which, so if you get rid of this R, then of course there is no randomness. So you'll get a deterministic yes no answer, and that answer should exactly be correct with respect to whether x belongs to L or not. So basically we need to from this build another circuit which will give the correct answer. How might we do this? Okay. So let me just pull this up a little bit and then try to do it in that corner here. So let me leave this here. Let me erase this calculation. So any suggestions how you might get rid of this R? Let me try to walk you through this. So what we know from this is that if you fix an L, take any fixed L, we really know that an overwhelming percentage of the R's are going to give you the right answer. Basically all but 1/4 to the n will give you the right answer. Okay, let's just write that down. For each fixed x of any length, of length n, all but 1/4 to the n fraction of random coins R yield correct answer. Is everyone agree with this? Right, because if x is in L, the fraction which gives you the wrong answer says x naught is in L is at most 1/4 to the n, and the same thing is true here. If x is not in L, at most 1/4 to the n will make you say yes. So for every x, most of the R's are good. But how many x's are there? How many x's are there in total? 2 to the n. Right? So now for each x, you have a 1/4 to the n fraction of R's which are bad. So how many R's can be bad for some x? Just counting, right, or counting or union bound in probability. So you can think of in terms of like matrix. Think about x's here and R here, and you put a cross mark if that R is bad for a particular x. So we know that each row has only 1/4 to the n fraction of x's, but there are only 2 to the n rows. So the percentage, the fraction of R's which are an x or bad for some, maybe I should not x and this x, let me call it bad. So the fraction of R's which are b for some x is at most 2 to the n times 1/4 to the n. You simply sum up the b's in every row, and there are only 2 to the n rows. Which means that an overwhelming fraction of R's are in fact simultaneously good for all x, because the number of x's is much smaller. That's why I made this, like, you might have wondered why did I put this goofy -2 there, just to make this look a little bit nicer. Okay, so is this, can I elaborate on this? This is just the union bound. If you want, you can think about it as a probability thing. So you can think of a random R and you can say the bad event is that it makes a mistake on x. So the probability of that bad event bx is 1/4 to the n at most. Now we can ask what's the probability of the union of these bx's, which is that you're bad for some x, and that is at most the sum of these probabilities. Okay, you should know this union bound. Probability of union of events is at most the sum of the probabilities of the events, and there are 2 to the n events, each with probability 1/4 to the n. So you're not going to, so the total probability of some bad event occurring is 1/2 to the n. Okay, sorry I didn't write most of it, but it's just the union bound. Okay, so let me at least write, say by union bound. Probability over R, there exists an x such that mxr is wrong, is at most 2 to the n for the number of x's times 1/4 to the n for the probability that for that particular x R is bad. So this is 1/2 to the n. So this says that most of the R's are simultaneously good for every x, which in particular means there is some R which is good for all. This is the probabilistic method. So how do you prove? Again, what was the issue there? We had this randomness there. We don't like that. We have to get rid of that. So the whole idea here is to find some R naught to which you can hardwire those R inputs such that regardless of what X is, the circuit will give you the right answer. Okay? And again, you don't care about finding this R naught. That's the thing. It can, I just have to prove this exists, because then there will be a hardwiring of those inputs to R0 which will give you a circuit. I can't find that quickly. In fact, nobody knows. If you did that, you'll be basically proving BPP is in P. Okay? But I'll prove there exists that R naught, and then I'll hardwire. Okay, and that's what this says. And the probabilistic method, and we use the probabilistic method to say such an R exists. Okay? So basically, finishing this proof, hardwire these such that mx R0 equals indicator of whether X is in L or not for all X. Okay, again, if this notation bothers you, I'm just being lazy, saying mx R0 is correct for every X simultaneously. So you just I proved there is such an R0. In fact, most R0s will do the job, but I can't use most and I can't use randomness. I need to find one deterministically. I don't know how to do that efficiently, but I have proved to you that exists, so we'll just hardwire it. Yeah.
So you proved that there exists now, but that is always true?
That is good for all inputs of length n.
But just from the fact that its probability is less than, isn't that still?
Yeah, so this probability that, okay, let's take so the probability that exists in X such that mx is wrong is at most 1 over 2 to the n. So probability over R that for every X mxr is correct is just the complementary event, that is at least 1 minus 1 over 2 to the n. So it's in fact all you need is that it's positive, but I've actually proved that it's close to 1, the probability. Right, again, what did we prove here? So probability over R for all X of length n, mx R is correct. This probability is at least 1 over 1 minus 2 to the n. So in particular, there must be an R such that it's correct for everything. And all I really needed is this is more than 0, but I actually said it's close to 1. Okay, so it's not a difficult proof, but it also says that really, it almost feels like BPP is not that difficult. Right, so, whereas NP, we don't think it is in P/poly. Okay, and I believe on Thursday you will talk about polynomial time hierarchy. There is some formal evidence you can give that it's unlikely that problems like SAT have polynomial size circuits. Can't prove that it doesn't, but we can give evidence it doesn't. BPP has this, and this maybe can be viewed also as some evidence that it's kind of closer to P than it is to NP. All right? Okay. So last 20 minutes or 15 minutes, I will say something about why people believe, or what have people done which lets them to believe that P is probably just BPP is probably just collapsing to P. Okay, but any questions about this proof or any other part? Okay. So this last part is just supplementary and just for fun. So let's do it. Oh, there's one more board down here. Wow. Okay, but that'll cast a shadow, so I'll just do this. So I will now talk about de-randomization. The phrase, as the name indicates, is really removing randomness. So and really the conceptual principle here is that, so what is randomness after all is a very philosophical question, has been investigated in variety of contexts, but really when it comes to complexity theory, something really the big insight, the conceptual thing is that something can be random if it is hard to tell it apart from a random string. Somehow, again, this is the complexity view of what randomness is, which is central to this de-randomization, but also extremely important in cryptography. You build these block ciphers, pseudo-random generators, really with this viewpoint that you're creating something which is completely deterministic, but it looks completely random for anybody who doesn't invest a lot of time. Okay, so this is very vital in cryptography. In fact, without randomness, there is really no cryptography for this reason. If, for any sensible notion of security, you can only meet that notion if you have randomness. I mean, that's a different aspect of randomness we are not touching upon here, which is also why, even if you might wonder, oh, we went through all this trouble, and if BPP equals P, why bother about randomness? Well, first of all, we haven't proved that, and there are some fascinating connections here. And in particular, some of these objects in de-randomization prop up in cryptography as well. So hardness implies can eliminate randomness. So which is sort of as easiness. So there is this sort of duality where if something is hard, you can make something else easier. So we can assume something is hard, and then you can actually de-randomize and remove randomness and make algorithms out of it. Okay. Okay. Okay, in fact, so here is a theorem. So Ryan told me that he has hit you guys quite hard with the ETH, which is sort of a modern souped up assumption. So what was the ETH? Let me just remind you, the exponential time hypothesis. So the P versus NP hypothesis is that 3SAT is not in P. Okay, but as long as we are making conjectures, why don't we just be as bold as possible without saying something ludicrous? In that spirit, ETH, okay, one succinct statement is that 3SAT, so there exists some epsilon naught greater than 0 such that 3SAT is not in time 2 to the epsilon naught n. Okay, not only is it not in polynomial time, it's not in time, say, 2 to the n over 1000. Let's say that's the ETH. There is some. So basically, the true time complexity of 3SAT is not only is it not polynomial, it's really 2 to the omega n. Okay, so time complexity of is 2 to the omega. You really need to invest 2 to the. I mean, there are faster algorithms which do better than 2 to the n, right? 1.34 to the n or something is the current record. So you can do better, but all those things are only chopping off a constant in the exponent. So this basically ETH says that you're not going to have an algorithm with running time 2 to the square root n, 2 raised to square root n for 3SAT. Okay, which really for practical lengths could be a big difference, right? So if you have say 1000 variable thing, 2 to the square root 1000, like 2 to the 30 would be a very feasible runtime today. 2 to the 1000 is not. So this actually has practical relevance as well. But the conjecture is that in the worst case, you have to invest these things. So more or less, it will be nice if you could say ETH implies P equals BPP. Okay, morally that's what this theorem says, but there is an important and significant difference, which is that so if you replace time complexity by circuit complexity, that's a very strong hardness. So note that if you have an algorithm running in time 2 to the n over 5, sorry, if you have an algorithm running in 2 to the root n, then you also have a circuit family of size 2 to the root n. Because by what I said, you can take a Turing machine and compile it into a circuit by just blowing up the time by a quadratic factor. So 2 to the root n square is also 2 to the 2 root n. That's also 2 to the order root n. So certainly, if ETH is false, then you will have small circuits as well. So the stronger assumption is that it actually requires big circuits. Right? So let me just write this down. If 3SAT requires circuit family of size 2 to the epsilon naught n, let me just call this 2 to the difference gamma naught n for some gamma naught greater than 0, then P equals BPP. Again, this is a stronger assumption than this, because if this assumption is true, then certainly you cannot have a runtime which is better than 2 to the omega n. Circuits are more powerful than, I mean, you can take a Turing machine and convert it into a circuit with a quadratic blow-up, but there is no such thing in the other direction. So this is a very strong assumption. I mean, this says that, I mean, in particular, for example, realize that every language trivially has a circuit family of size 2 to the n, or n times 2 to the m, because you can just write down the truth table, right? You can just write down the big tree which computes it. Whereas certainly there are languages whose time complexity is much more than exponential time. There are languages which will take 2 to the n time and so on. You can just build these, I mean, artificial languages by the time hierarchy theorem. So in some sense, this is really saying 3-SAT is almost maximally hard. Everybody has a circuit family of size 2 to the n, and 3-SAT somehow is so hard that you can't really do much better. Okay, this is like an extremely strong assumption, but the striking thing about this is that if you make this assumption, which has nothing to really do about randomness and so on, then you get an easiness consequence. So you make, if something is hard, something else is easy. Okay, so that duality is very striking and nice. Okay, and really the point is 3-SAT, and the actual theorem doesn't really require 3-SAT. It doesn't require this particular language. If so, I'll just write that down just for reference. So you can really weaken this assumption, which is very strong, slightly, while still keeping it very strong. Basically, you will say that if some language, so the reason this is a very strong assumption is that 3-SAT is in some sense easy, because it's a language in NP, right? Whereas we know in the zoo there are things which are much higher up. So actually you need languages with such maximal circuit complexity which can be quite far high up, almost in exp. You know, I more or less say exp here, but let me be accurate and say it's not really exp, it's some class called E, which is basically time of 2 to the order n. Recall that exp is 2 to the poly n, E is 2 to the order n. Okay, but if it's confusing, you just think of this as. So really you just need to find a language in exponential, in a big class here, where we think there are things which are hard, but we need to find a language there which has very, very high circuit complexity. If such a language just exists, then P equals BPP. Okay? Yeah?
By time hierarchy, there's always, so what does this have to do with?
No, if there is some language in E which requires large circuit complexity.
But can't you always construct some artificial
Which has large circuit complexity? Exactly, I was going to be my next remark. Perfect. So the point is, just by a counting argument, you can say how many circuits are there of some size, like 2 to the n over 2. You can just count that. It's just counting graphs. Okay, and that will be definitely quite a bit smaller than the total number of functions on length n. So in fact, most functions, if you fix a particular input length, most functions of that length will require circuits basically of maximal size, just by counting. But the point is, you have to find a sequence of those functions which all patch together and are easy by a single exponential time algorithm. So it's not hard to find languages which have big circuit complexity. In fact, I can make this gamma naught basically like 0.99. So there are languages whose circuit complexity is 2 to the 0.99 n. But the difficulty is I have to find such a language which is not way up there, and that's the challenge. So I need to find it inside exp. So for example, just yeah, so that's the, yeah, and then, on Thursday I believe you'll see the polynomial time hierarchy. So there is an analog of that in the exponential time world, and so you can find languages with maximal circuit complexity, but they'll be a little bit higher up, even above these guys in this zoo, which I have not drawn, but you want them somewhere here. That's the difficulty. I mean, the whole game, the reason circuit complexity, all these things are hard, is that we want to take some function with structure, like 3-SAT or something which is in some sense easy, and prove that yet it is not that easy. So you have, If you're just cooking up crazy functions, non-constructive, with no upper bound on where they sit in this, then hard things abound. But it's the fact that you have to find these hard things inside at various points in this hierarchy which makes the whole game challenging, because you're trading off some aspects which make the function easy, if you could call belonging to X easy, but it does say that it has some structure, versus saying it has large circuit complexity. Okay, so I have only 5 minutes or so, so I won't. I mean, this is a very deep theorem. It was proved around 98, and it uses various very nice ingredients. So at a very high level, this theorem, I mean, now I'll just give you like buzzwords, some sort of 1,000 feet snapshot of how this is proved. Really, it's a deep theorem which is proved in 2 major steps. Okay, so the first step is worst case hardness. Again, I won't be precise with some of these terms. So the assumption you make is a worst case hard assumption. So we say that this problem doesn't have a small circuit which gets it correct on every input. So that's the kind of assumption. And let's not worry about this E. Let's just say 3-sat is hard. It's like, from that, you convert it to a strong average case hardness. So what do I mean by that is that you somehow say that if you're hard in the worst case, namely it's hard for you to get every answer, every input right, in fact circuits of this size are going to be wrong on almost, basically they're going to be as bad as random guessing. Right? For any problem you can get the answer correct with probability half by simply guessing yes or no randomly. So half is trivial. Basically you can amplify the hardness from worst case to average case and say that really there are problems in E which are so hard that if you give me a huge circuit, it basically is as bad as random guessing. So that's how hard these functions are. Okay, that's the first step. And there are a couple of proofs of this. The one I like and is also connects to uses via coding theory. So uses something called list decodable codes. Which is a topic which is quite close to my research interest, so which I like this first step quite a bit. And the second step, which is also very beautiful, but it's older. So this was the step which was done around the late 90s, and this is probably around 1990. This was you build some pseudo random generators. Okay. So I mean, I won't formally define pseudo-random generators, but they're really fantastic invention of complexity theory. They, as I said, they are absolutely crucial in cryptography. They are really the theoretical underpinnings of block ciphers and all these other ciphers people use. Okay, so this is really the 2-step process. Both of these are important, and this connection from the 1990s, early 1990s is not that hard. I mean, if I had, let's say, if I had one lecture, I could make a strong enough assumption here and show this to you in one lecture. It's a very clever construction, but it's not too difficult. So I won't tell you what the construction is, but I'll tell you what the pseudo-random generator is, which we are mentioning, and then we are done for the day. Okay, and if somebody is interested, just send me or Ryan email. We'll point you to references. As I said, at least the second arrow is not that difficult, in terms of technical things. But it just takes time to set it up because you have to define things formally and all that. And we haven't done those things, but mathematically it's not hard. So what one is going to do is this. So pseudo-random generator, I won't define very precisely, but I'll tell you the kind of object it's going to be. So it's the generator G, which is going to take a small string of log n bits, okay, and map it to a string of n bits. And you should think of n as the number of random bits an algorithm needs. Suppose an algorithm needs n random bits, rather than feeding it n completely random bits, what you can do is that you can, so G of S, so you can think of the input to S as a seed, a short seed, okay, of only log n bits. And really the idea of the pseudo random generator is that when I pick S to be a random seed of length log n and I apply G, I'm going to get a string which is definitely not random, because even its support size is only polynomial, right? Because the input, the domain has polynomial size, because it's 2 to the order log n, it's polynomial size. This is 2 to the, this is a huge space, and so this is the space 0, 1 to the log n. Then you're mapping it this, so you're going to really map to a small space here in 0, 1 to the n. And yet, if you're a machine running in polynomial time, you can't tell the difference for a string randomly picked from the shaded tiny part versus a string picked uniformly at random. It seems counterintuitive, how can that be? But the key point is you are supposed to tell whether the string is pseudo random. Pseudo random is just a string which is the output of this generator. You have to tell if a string is pseudo random or completely random, but of course you can do that if you had lots of time, because you could literally try every, this G should be computable in poly time. Okay, so you could literally try every possible S, there are only polynomially many of those, compute G of S and see if you land to their sample. So I'm going to give you one sample and ask, hey, did it come from the output of G or is it like genuinely random? And of course you can tell that by literally just computing the image of G. But that's going to take you some polynomial time, but maybe I restrict you to time which is only n. And then in that setting you cannot tell this difference. So output looks, so basically G, output of G looks random to, let's say, you know, n square complexity machines. I'll be just vague here. And since I'm trying to fool a randomized algorithm which say runs, which uses n random bits and runs in n square time, I can cheat this randomized algorithm by not giving it pure randomness, but just giving it the output of a pseudo random generator. Okay, and the last point is why do you, but that still seems to need randomness because I have to give the seed randomly. But the point is that the seed is short, so there are only log n bits, so the number of possible seeds is polynomial time, is totally polynomial, so I can literally run this randomized algorithm with R, its randomness initialized to G of S for every possible S. So I can, so really the idea is we had this naive strategy of looping over all R's. Now I only have to loop over all S's and feed the algorithm G of S. And somehow this algorithm cannot tell the difference between this experiment and running the same code with completely random. So basically you're able to fool efficient computation by something which is definitely not random but looks random to such machines. And the reason you're able to build such things is because there are things which are hard, which is this whole connection. Okay? And this is exactly, with different parameter regimes and different requirements, this is exactly what goes on in cryptography as well, where you might want to map n bits to 2n bits, where the output looks completely random, so you can use that as a cipher. Okay, but here the crucial point is you're stretching log n bits to n bits. It's an enormous amount of stretch, but you only try to fool relatively benign machines which are not running in too much time, because you're just trying to fool your randomized algorithm. Whereas in cryptography, you try to fool. So one major difference is that here the generator can take more time to run than the algorithm you're fooling, whereas in cryptography you definitely don't want to do that. You want to run quickly and you want to fool adversaries who can spend a lot more time than you. So that's sort of a slightly different ball game of parameters, but for us this tends to suffice. Okay, so let's stop there.